Like this. Okay, good morning everyone. Thank you very much for the opportunity that you've given me to talk to you today about ESMO. ESMO is the European Student Moon Orbiter, and it's run out from the ESA Education Office, who you've heard about earlier today. Seem to be behind a lot of good activities. This is the fourth in the series. I think many of you here will be familiar with the activities in the Education Office, being involved, I believe, in the SETI Express, also currently involved in ISAO as well, and ESMO is the next step on. So ISAO is focusing on an Earth orbiter, and ESMO is focusing on going to the moon. So the objectives, there's two slides on objectives. One are the sort of the technical, and then there's another on the educational. So effectively, what ESA want this to be is a very hands-on programme. So we're going to launch the first spacecraft to the moon that's been designed, built, tested, and then operated to the moon by a team of universities across Europe. So we're going to get it to the moon, and then the focus will be on how we can maximise the educational, the outreach, return, and then the science and sort of technology demonstration element. So launch, I'd say early 2014 would be fantastic. Realistically, we'd like it to be by early 2015, but that, you know, that looks feasible. So the educational objectives are very simple. It is to try and get as many students involved and interested in the general STEM activities, but specifically to bring them in and lure them into the space industry, and also to give them the experience so that they're turned out into the space industry as good people that can work across the sector. So it's about preparing a well-qualified workforce for future ESA missions. So it's very much hands-on, and so I'll go initially into the technical sort of baseline, give you an overview of what it looks like, and then we can talk about the programme and the roles and the responsibilities and where we are with that. Okay, so this is the overview of the baseline. There are some driving mission requirements, and actually it's funny how they change. They've changed already over the last year. The one thing that does remain fixed is the fact that we are aiming for a shared launch to GTO, and that's simply because we're going to be a secondary passenger. ESA are currently trying to agree with various launch agencies what the options are, but it will be a launch to GTO. So ESMO, as a spacecraft, needs to be capable of getting itself from GTO to the moon. So we've been looking, I think it's the Ariane 5, the Falcon 9, Cyclone 4 and the Soyuz are the options that the spacecraft is currently sort of designed to try and be compatible with launch on. So a number of trades have been done over time. For a number of reasons, chemical propulsion system is the current baseline. One reason being that there's a large amount of ESA-supplied flight hardware, tanks, thrusters, very high-value items, which are there from previous projects for us to use. The other driver for not going down things like the electric propulsion route was time spent in the radiation belts, and there were some other issues as well. And so the baseline is a biprop, and I know that I think from your Phase 3 C mission, there's some people there with some experience of biprops, which we'd love to talk to you about afterwards. But anyway, so the selection of the final lunar orbit, I wish that was now a driving requirement for us, because we don't have the luxury of being able to optimise the lunar orbit. As you'll see as I carry on talking, the technical sort of challenges of the project are such that actually we just need to get to lunar orbit. And then it's a case of trying to looking at the payloads you can take and then maximising the return from them. So that's less of a driver at the moment, really. So the mass being one, there's basically the ESA-supplied hardware. We've got two flight spare tanks from the GOVA-2 mission. They have a certain qualification level, which is actually placing a limit on the amount of propellant that we can carry. That then feeds back into the total mass of the spacecraft, so that's constraining us on mass and delta V. So what we then have is some complex mission analysis work going on by members of the team, trying to really reduce the amount that we need to do the various phases, the transfer and lunar orbit insertion. So there's that relationship there that's really constraining us. And more recently, what we've also seen is that the attitude and orbit control system, looking at the different thrust levels, some of the firings are incredibly, or quite big, quite long. Others are of the order of tens of seconds, so that's then placing additional constraints on the system. So that's the real driver, I would say. Then on the technical level, then you've got the additional driver of cost and schedule. This is truly Cosmos on a shoestring kind of mission. It's not got a very big budget. As you will see, a lot of it is going to rely on, and it's very much, again, very similar to some of the work that you've done previously on your Phase 3 satellites. It's about getting a hold of beg, stealing and borrowing almost, whatever you can to try and get you there to the moon. Actually, I don't advocate stealing, I'll add. But it's very much about getting hold of what you can and just trying to engineer it so that it works and takes you there. So limited budget, and then the schedule is obviously, you're trying to keep the schedule reasonably constrained so that your costs aren't escalating over time. So those are the drivers. The design philosophy is fairly straightforward. You're designing it so that no credible single failure can lead to loss of the mission, and you're looking at a mixture of hot redundancy where you can, cold redundancy, or hot redundancy where you have to, I should say, on things like your receivers, for example, cold redundancy on the other items where you can, and in a few cases where we haven't been able to, we'd be looking at things like graceful degradation so that we are not having a failure leading to loss of mission. Obviously, there are certain things that have to be single string because there's no viable alternative. What we're aiming to do also, there's a lot of work gone into the sort of concept of operations and looking at failure detection, isolation, and then recovery from that. And basically, we're trying to go for a fail-safe strategy because it's just simpler, easier to implement. But as you will see later, we've got some critical manoeuvres when we're trying to get out to the moon, and there we are having to look at what, failing operational to just try and maximise our chances of getting to the moon. Margins approach, again, is fairly standard in terms of just assigning a margin depending on the maturity of the systems. Okay, we've got a number of payloads that are in the baseline and one payload that's a current backup. The main thing to say here is that the narrow angle camera is a requirement on us from ESA to fly, and that's for the outreach aspects of the mission. They want to be able to include schools who can then task the satellite to take images at certain points on the moon and then that be returned to them. The others are there for various reasons. I think the lunar internet is probably of interest to some of you here in the room. And then we've got things like the MIWAs as a backup payload. I'll come on to talk about potential payloads towards the end as well. So that's just there to show you what's in the baseline and to show really that there are 4 payloads budgeted for when we look at things like the mass and the power budgets. Okay, so launch to GTO. The moment we have, we're constraining ourselves to trying to spend a month or less in GTO simply because the radiation dose in that radiation environment is horrible. We want to minimise the dose on the components. So we'll do just the essential platform commissioning in that month, and then it will be a case of starting your firings to basically raise the apogee so that we go out to either an L1 or an L2, basically a weak stability boundary point from which we can then perform the lunar orbit insertion manoeuvres. That we expect that phase will be about 3 to 4 months from the analysis that's currently been done. Operational orbit, we're aiming for 6 months. At the moment, it's a very highly elliptical orbit. It's about 300 kilometres at perihelion, and it's about 1,600 kilometres at the apoloon. And then if we can get into a frozen orbit, who knows, we may be able to extend that lifetime, but that's the current plan. And then end of life, it would be a case of natural decay until surface impact. So that's just to give you an overview of what I've talked through on the previous slide, and really to show that sort of end-to-end, you're looking at about 11 to 12 months of the lifetime from launch into GTO. Concept of operations. At the moment, we have a primary station Via Franca, which the ESA Education Office are trying to bring, well, have donated into the project. This is a 15-metre dish. We're also trying to look at the use of the rest of the sort of ESA track system, just to give us that better coverage. So the ESA primary station is the baseline for the sort of LEOP and transfer phases. We then have another station, which is the Reisting station in Munich, which is actually a 24-metre dish, and it's currently being upgraded by the Munich university team so that we can then use that for payload operations from lunar orbit. So we've also got a primary mission control centre and a backup mission control centre as well. I mean, obviously here, well, I won't say it here, but you'll see later on, I think, from a link budget perspective, when you're out at your 1.5 million kilometres point, it would be nice to have more of the larger stations, such as the 24-metre one, to improve your link budget. But getting those sort of stations nicely spaced around the globe is part of the next challenge that we can look at. Okay. Basically, as I said, a lot of work's been going on the concept of operations. Where we're coming from really is we've got a concept that SSTL developed for the JVA mission, and we've been working with the university teams basically to work through that and trying to develop that so specifically for the ESMO mission. And I think really that's just showing that we've split it into modes. We're working through in detail on each of the modes, looking at what could happen and what the strategy will be for the spacecraft to recover from it. So I'll leave you can read that offline. I think that's probably enough. What you see here actually is some of the student team members at SSTL for a workshop which was held in, I think it was the end of last year, working on the FDIR strategy. So that's just showing it's in action and it's happening now. Okay, on the spacecraft side, because of the mass constraints, we've had to go for quite an open structure actually. So you've got an aluminium honeycomb central thrust tube and a series of struts and panels basically coming off from there. At the moment we're around the 265 kilogram maximum mass, and as I sort of indicated earlier, that's not really being driven by your maximum launch mass. At the moment that mass is being driven by it will always be driven by the amount of propellant we can hold in those tanks. At the moment, the payload capability is of the order of a few kilograms, but we've obviously got a lot of margin built in the system, and let's hope that the things come down and we can increase our payload capacity. We've got a plan for 2 body-mounted solar arrays. We've been triple junction gallium arsenide cells have been donated into the project from MCOR, so they will be used. We've also got, on the power side, we've got ABSL have donated lithium-ion battery, which we'll also be using. We've got 3-axis AOCS and some donated sun sensors and gyros have been donated by SSTL to the project. Star trackers are being built by ISA in Toulouse, university team, and we've got some cold gas thrusters and an attitude interface module which we're pulling together all the sensors and actuators. On the comm system, it's S-band. At the moment, the baseline is based around 6 low-gain antennas, which again I think you're probably familiar with. They're coming from the Rochelaw team in Poland. I think they're flying on your ISS experiment and probably flew also on SETI. So that's the baseline that we've got at the moment, and ESA have just very recently been able to confirm that we actually will have access to the Smart 1 flight spare medium gain antenna, and the Gochi medium gain antenna, and that we believe is going to really make a big difference for us at the WSB, and the link budget analysis is going on at present to try and see where that gets us to. The onboard data handling system is being basically managed and designed, built and tested by the university team in Maribor. And it's based around the CAN bus, and we've also implementing an attitude safety module, which is again quite similar to the design approach we used on GOVA2. So I think that's I missed out the big one, the biprop, primary propulsion system. The time of this, well, the original baseline going into the preliminary design review was to look at a fairly standard performance, more like sort of 286 second ISP. Unfortunately, the way the system's going at the moment, it's looking like we may need an even higher performance system. So you're looking at a dual mode biprop, very much like the ones you would use on a geo spacecraft, but we'd be potentially looking at a hydrazine option. So from a cost perspective and an options perspective, that's not great, and we're looking at so that's a big issue for us at the moment, trying to work out, do we really need the highest performance chemical propulsion system on the planet? Okay, so, well, not quite, but anyway, in terms of biprops, it's the highest performance you can get. So that's just to give you an overview of what the system looks like. I'm trying to think if there's anything. So I think, yeah, the main thing is that at the moment this propulsion system architecture is being reworked, trying to see what we can do to try and maximise our delta V budget. And everything else is ranging is something I'm not going to talk about, unfortunately, because it's very early on in the design process. Ranging is a function that the guys at Rochelaw will be working on for ESMO. My understanding is that because we're going to be compatible with ESA-TRAC, most of their systems are still on the tone ranging sort of setup. Only some of them have gone into the sort of regenerative ranging aspect. So I think we will probably be tied to the tone ranging side of things. But as it's all there and set up, it hopefully isn't going to be an additional cost to on the ground seg. Okay, I think that's all on there, and that's just showing you what it looks like. And actually, if you all wait till in a couple of months, we'll be producing a new paper on ESMO, and it will have completely changed. We've just had preliminary design review, which is a great way of focusing everybody's minds and getting them to really communicate. And I think, as I say, a number of late-breaking issues that came up as we went into the PDR have actually meant that we've had to do an awful lot of work in this closeout phase that's looking at, for example, one of the main drivers for the change in configuration is to get the centre of gravity a bit more stable and towards the centre of the spacecraft, because what we were seeing is the way the tanks were being depleted, it was causing our AOCS guys a big problem. So yeah. Couple of months, new paper, you'll see the new design, and it's not drastically different, just an extra panel or two and a few things rejigged. So there you go. Mass budget, I won't dwell on it really. So I mean, it's all going to be updated. We're doing the sort of next level of detail, but I think the key point is that we can't exceed this 265 kilos. And we've got the margins applied at the unit level, got your margin at the system level, and it's now a case of going into that detailed design and seeing, you know, if we can bring the margins down and get some more payload on. Power budget, I think all I will say here is that the team have looked through the various phases. They've looked at what's required. It's a short lifetime mission. There will be a certain amount of hammering of battery going on at various points in the programme, because as you can see, when you've got some of these manoeuvres, you've got high power requirements. But generally speaking, power budget looks okay, but I will caveat that by saying subject to the heater power requirements being specified in more detail. So I think at the moment power budget isn't such a big concern. It's the mass budget that's driving everything. Link budgets. I guess you guys probably wanted to see a whole load of link budget analysis. I'm sorry to disappoint here, but basically the team are now working on looking at the inclusion of the medium gain antennas, because what we were seeing is at the weak stability boundary point we were getting about 2 kilobits per second of downlink data rate, and the aim is to just see if we can give ourselves a bit more, because I presume at that point if we're having to do any sort of failure resolution, you're going to need to be getting your telemetry down and dealing with it. But at the moment, so you've got near, I think also the other problem at the WSB is the nulls in the antenna pattern, and I believe that the Rochelaure team are looking at that and seeing if they can modify their antenna design. But basically, apart from the WSB, it's all looking reasonably healthy. We've got, as I say, we've got the 15-metre dishes, you've got your 24-metre dish at Munich, and it's amazing how many 30-metre dishes are now popping out and sort of notifying us of their existence. So we'll be certainly looking to bring on board anyone that we can to just get good coverage throughout the mission. Okay, so that's it on the sort of just the baseline, an overview of the baseline. I was just going to talk to you a little bit about the programme itself, because it's very challenging, it's very interesting, and just like to sort of clarify the roles and responsibilities. We've got a very big team. So ESA is the ESMO customer. They're providing us with this flight opportunity to the moon. They're also providing us with the technical support throughout the programme, throughout reviews and workshops. And as I've also said, they're giving us a lot of flight spare hardware, and more keeps coming up. So that's a good sign. One of the key things here is that it's not a typical sort of customer-supplier relationship, and it's very important when you're working on. It's technically very challenging. It's programmatically very challenging when you've got such a distributed team. It's on a shoestring budget. Can I think of any more challenges? I can't at the moment, but I think that's enough. And so working together as a team is obviously critical, and I think you guys know that already from your own experiences. So it's good to see that it's working out very well with ESA and SSTL working closely as partners. The same goes for us working with the network of universities. So Surrey's role on ESMO is effectively we're the prime contractor on behalf of ESA. We're leading the systems engineering, and we're also providing industrial mentoring to the university teams, and that's regular communications, but also bringing people in for internships to, at the right points in the programme, really, to help them. So it really is, again, we're not treating the teams as subcontractors. It's about working together. They're basically a part of the team. The network of universities have incredible responsibilities. Effectively, each university team is responsible for the design, the development, the build, the test, and then the support of operations for their subsystem. So that's no small task for the teams. Each university has got a professor, a certain amount of academic staff, and the student team. The other challenge for the teams, of course, is that they are having to find additional funding, because what the ESMO project provides an amount to each team. In some cases, it's literally for covering the internships and for covering them for going to the various workshops, and they're having to go out and do a lot of beg, not quite stealing, and borrowing to try and make it work. One of the things we've certainly found is that having a good, strong team with a professor who is very hands-on and making sure that the continuity of knowledge is passed on between the teams is key, because working with university teams where they've got their academic schedule, they've got their exams, that's why they're there in the first place. And then there's often, if people are using a lot of undergrads, what you're finding is they're there with you get about 9 months of work with the team, and then they're gone. So it's a headache from that perspective, and so having a sort of very close core within the university is obviously proving to be very important to that. Okay, so that is a list of who is involved on the university side. There are some names, I think, again, you've already mentioned, I think the University of Vigo, so they're responsible for upgrading with ESA and then operating the Via Franca ground station that ESA have donated into the project. But you can see there's a real spread of universities around Europe. So I don't know, I'll leave you to have a look. But can't name more. Okay, so I'll move on to the next one. That's to give you an overview of the programme. Really, it's just showing what I've explained. You've got your customer there who's responsible for procuring and providing the launch, SSTL doing the project management, and that's the sort of task that we're doing alone, whereas with the system engineering we've actually brought on board the University of Southampton and they're working with us on that. So we're leading it, but they're using it as they sort of have 2 interns coming and spending a number of days with us every week, and they're sort of doing hands-on learning by actually being part of the systems engineering team and doing it. And then this is showing you what I said before, that basically the universities are doing all of the build, design, build and test activities, and what SSTL and ESA are doing there is providing them with the sort of mentoring and advice and support workshops to allow them to do that. Yeah, so that's just an overview, a graphic overview, really. Where are we in the programme? Well, there was a Phase A study done prior to 2009, and that was being done with the ESA Education Office and the network of universities. SSTL joined the programme towards the end of 2009, and since then we've completed the system requirements review, the system definition review, and we are currently in the preliminary design closeout phase. And I will say it's one of the most amazing things to me was actually we had this huge PDR data pack to deliver to ESA, and we managed to sort of get the various iterations done, coordinate with all the teams to deliver that on time, which I think when you know is a real credit to the university teams working on the programme, because it's a pretty hard task for industry, I think, just to deliver an entire ESA level data pack. So that's been good, but as you can see, we delivered that on the 28th of March. We had the co-location with ESA where you go through and discuss all the various actions and comments raised, and we're still in the process of closing all of those out. So we're hoping around the September time frame that we can draw a line under the preliminary design phase and really start moving forwards into the critical design of the programme. So there you are. So I think, as I said previously, January 2014 would be nice. Realistically, January 2015 we'll take that. Thank you very much. I think the challenges and approaches is definitely something that I think you guys will have experienced yourselves. Applying small satellite design philosophy to a widely spread team is actually difficult. We're making the best use that we can of the technologies available to us, the Skypes and the Makogos and all of those things, but it's still hard. It is much easier if you're all sat around a table in a room, and we've certainly seen that from the workshops that the student teams get more out of it and we get more out of it. You make the progress. So it is a challenge, despite the best efforts of technology. So the other thing, as I mentioned before, delivering a space mission on academic schedules is hard. You know, our guys aren't used to having a 2-month outage whilst the student teams while someone's off doing their exams, but that's part of the reality of the programme. So that's why having a mixture of your PhDs, your research assistants, your undergrads, your MScs is important. So having that teaming right throughout is one of the things, the ongoing goals. And then, of course, there's all the technical challenges of getting to the moon, which I sort of almost fall by the wayside when you look at the programmatic sometimes, and you look at the things like your budget problems. So I think those are the challenges. The approaches are, I think, again, regular open communications are vital. The workshops, the training, the internships, the good links into the universities, the talking to the professors, but the universities also needing to show that ownership as part of the programme and really grab it by the horns and drive and run with it. We've got an excellent set of teams, and it's about finding the teams that have got the core skills that can do the job. We're using our industrial mentoring, we're using our expertise to try and put as much into the programme as we can. ESA are also doing the same, using their experts, and as I said previously, it's really about trying to work as partners and not worrying too much about the contractual details and just getting on with the technical work in hand. So those, I think, are the challenges, and these are the approaches that we're developing to try and deal with them. And I just wanted to, I've got, I think, just one or two more slides, so not going to keep you from your lunch for too much longer. But I'd like to say that opportunities, I think with a programme like ESMO, it's always about enhancing what you've already got, and it's always about trying to improve what you've got and further maximise what you're getting in terms of your outreach, your return for science or your return for technology demonstration. So, you know, I think there is scope to include more people, more expertise, more mentors, more experiments, and certainly if you're looking at software experiments, then I would be great if you could forward on any ideas you've had, and we would look at how we can implement them on the programme. Also, if you've got some nice small payloads that you think might be worth putting onto our backup list, let us know, because it's great that if we can look at them now, try and identify what the likelihood is, and at least have them on that backup list, then hopefully, you know, we can take more people with us to the moon and benefit from the support of communities like the AMSAT community, which would be fantastic. So the final thing I'll say is we keep having to remind ourselves, although the moon's there and it motivates us, it is about the journey, and you know, it is about people joining us for the ride, really, and learning and benefiting and sharing the information. So that's all I had to say, apart from thank you to everyone on the project that's working with us, the sponsors, and thank you to everyone for listening. Okay.